So for the discussion today, we'll be doing lecture 13. So title is Taylor and Maclaurin series. So our goal is to find Taylor or Maclaurin series for some elementary functions that we know. And also we will use the concept of approximation using the Taylor polynomial or Maclaurin polynomial in order to approximate values using the um, functions and its corresponding Taylor or Maclaurin polynomials. So let's start with this recall. We recall the definition of a Taylor series. Okay. So if f is a function which has a power series representation at a, then it is of the form given by this. So you have f of x, sum of the nth derivative of if f evaluated at a over n factorial times x minus a to the n, where n runs from 0 to plus infinity. And in here, the equality is true when the absolute value of x minus a is less than r. Okay, so if we expand it, if we expand this series here, you will have f of a plus f prime of a 1 over 1 factorial times x minus a plus f double prime of a over 2 factorial times x minus a squared plus so on and so forth. And we call this representation the Taylor series expansion of f centered at a. Okay, so in here R is the radius of convergence of the series here, and the equality, okay, the equality of this function and this power series is only valid in this when this inequality here is satisfied. Okay, so f of x will be equal to this power series if the absolute value of x minus a is less than r, where r is the radius of convergence. Okay, of course, we can have the radius of convergence to be equal to infinity. So it means that the equality is valid for all real numbers x. Okay, so again, we call this the Taylor series expansion of the function f centered at a. And then we still adopt the convention that the zeroth derivative of f at a, this is just the value of f at a. Okay? And when the center is 0, then we call this expansion the Maclaurin series expansion of f. Okay? And then during your lecture, you saw several Maclaurin series and Taylor series centered at some center A. So let me show the uh, the common or the usual Maclaurin series that we see and we use in order to derive some other functions. Okay, so the first guy here and the third guy here, um, they are easy to memorize. So I hope you will memorize them by heart. And this guy here can be derived using the first guy. So the second bullet here can be derived using the first bullet here. And then I hope you also memorize the expansion, the series expansion for sine x or for cosine x. Okay, they will be used commonly in our discussion or in the future courses. Ln, the logarithmic 1 plus x, you can derive it using this um, expansion. But anyway, I think this one is also easy to memorize, so you can do that. Now, the inverse tangent of x, you can derive this using the second bullet here. Okay, so if you don't memorize the other guys here, the series expansion of some other elementary functions here, make sure, or at least be sure, where which function you will use to derive them. Okay? So anyway, let's go back to our slides and let us work on some functions here. So for the first problem, find the Maclaurin series for e to the minus 2x and use it to find the sum this series here. Okay? So to do this, we recall the power series representation or the Maclaurin series representation of e to the x. Okay? So e to the x, its Maclaurin series is equal to the sum, and from 0 to plus infinity of x to the n over n factorial. And this equality here, okay, this is equality here is valid for all x in the set of real numbers. Okay? So from here, what we're going to do to obtain the power series or the Maclaurin series for e to the minus 2x is to replace the x with minus 2x. Okay? So in here, for x element of the set of real number, e to the minus 2x, this is now equal to the power series from n equals 0 to plus infinity of negative 2x raised to n over n factorial. Okay? Or let us rewrite this. We factor the constant negative 2, okay, or the coefficient negative 2 here. So we rewrite this as the series from n equals 0 to plus infinity of, let us also separate the negative 1. So this will be negative 1 to the n, then we have 2 to the n, x to the n divided by n factorial. Okay? So this is the Maclaurin series for the function e to the minus 2x. Okay? Now, we want to find the sum of this series here. And according to this, we use the Maclaurin series for e to the 2x. Indeed, if you look at this expression, okay, and compare it with this series, we have negative 1 to the n, we have 2 to the n, and we also have n factorial. Okay? And then in here, we have 1 over 3 to the n. So we use that 1 over 3 to the n, okay, and compare it with x to the n, and we will know which x value we will use in order to find the actual sum of this series. Okay? So if we take now x equals 1/3, okay? If we take x equals 1/3, then this series here, then we have the power series, negative 1 to the n, 2 to the n, you have 1/3 to the n over n factorial, and from 1 or from 0 to plus infinity, okay? Or we rewrite this as the series from n equals 0 to plus infinity of negative 1 to the n, then you have 2 to the n over 3 to the n factorial. Okay? But this guy here, on the left-hand side, this is just your e raised to minus 2 times 1/3 here. Okay? Therefore, this guy here, the sum from n equals 0 to plus infinity of negative 1 to the n, 2 to the n, over 3 to the n factorial. This is just e raised to negative 2 thirds. So this is the exact value of this series. Okay? Let us now proceed to our next example. So in here, we want to evaluate e to the minus x squared dx as an infinite series. Of course, as it is, this guy here, we will not be able to evaluate this. Okay, at least at this level. Okay, at least at this level. But later on, actually, you will be able to find the value for this when you deal with definite integrals. Okay, when you deal with definite integrals with this integrand. But as an indefinite integral and at the level that we have right now, we will be able to do this only using infinite series. So what we're going to do is to start writing the Maclaurin series for e to the minus x squared. Again, using this representation here. So this time, we will replace the x here with negative x squared. Okay? So note that e to the minus x squared, this is equal to the series n equals 0 to plus infinity of, what is this? Negative x squared quantity to the n over n factorial. Okay? Or let us again rewrite this. We separate that negative. So this is the series from n equals 0 to plus infinity of negative 1 to the n. And then we now write x raised to 2n divided by n factorial. Okay? Therefore, we get the indefinite integral here. Okay? So the integral of e to the minus x squared dx, this is equal to the integral. And then we now use the power series representation or the Maclaurin series. So this is now sum from n equals 0 to plus infinity, negative 1 to the n, x raised to 2n over n factorial dx. Or this is equal to the sum from n equals 0 plus infinity of the integral. Let me bring out negative 1 to the n and also n factorial. Okay, so we have here negative 1 to the n over n factorial, and then you have the integral x raised to 2n dx. And this guy here, we just have the series from n equals 0 to plus infinity, negative 1 to the n over n factorial. And then we integrate this, we'll get x raised to 2n plus 1 over 2n plus 1, and then plus some arbitrary constant here. Okay? So let us just, well, you can rewrite this. You combine the n factorial with the 2n plus 1 in a single denominator. You can do that. You can also leave the final answer in this way. But I'll combine these denominators here into a single denominator. So series from n equals 0 to plus infinity, negative 1 to the n, x raised to 2n plus 1, all over n factorial times 2n plus 1. And then plus the arbitrary constant c. Okay? Okay? Now, for our next example, we want to find the value of the integral from 0 to 1 of e to the minus x squared dx correct within an error of 0.001. Okay? Correct within an error of 0.001. Okay? So, first, let us look at this. So we have this, the indefinite integral, e to the minus x squared dx. And we found that this is the integral, right? And now, on the next page, we want to find the value integral from 0 to 1 of e to the minus x squared dx, okay? So we use the indefinite integral on the other side here on this example, and we can now remove this constant. So we just have this guy here, okay? So in here, we will have the series n equals 0 up to plus infinity, negative 1 to the n, x raised to 2n plus 1, all over n factorial 2n plus 1. You evaluate this from x equals 0 to x equals 1. Now, first observe that this guy here does not have the constant term. The constant term is it's this guy here. But remember that when we do definite integral, the constant term just cancels with its own value. So this guy here does not have a constant term. So when x equals 0, the whole expression here will be 0. And then when x equals 1, okay, we'll just replace the x here with 1. So this is simply the series n equals 0 to plus infinity of negative 1 to the n over n factorial times 2n plus 1. So this is an alternating series. And remember, when we discuss alternating series, we also discuss approximation of the series using approximation of the alternating series, okay? Using the nth term or n plus first term of the series, okay? So let me just write this, alternating series, okay? So in order to find a value for this, okay, for this definite integral, which is correct to within an error of 0.001, we use that theorem, okay, the theorem of approximation, alternating series, okay. So if we have an alternating series, let's just say it's of the form negative 1 to the n v sub n, okay? And let us put s to be equal to the sum, which starts with 0, n equals 0 to plus infinity, negative 1 to the n pm. And then we put s sub k to be the kth partial sum, n equals 0 to k, negative 1 to the n b sub n, then we have the following approximation. The absolute value of your s minus s sub k, this is less than or equal to the k plus first term. Okay? Particularly, this is just your b, the b here. Okay? So we have here b sub k plus 1. Okay? So this is the theorem that we are going to use in order to approximate, okay, in order to give a value for this definite integral. So your S, this is your actual sum, okay? This is your actual sum. Your S sub K, okay? Your S sub K, that's the one that you're going to remove, okay? That's the one you're going to remove. And then it must be less than or equal to B sub K plus 1. Okay? So if we now let S equals this alternating series, negative 1 to the n over n factorial to n plus 1, n starts from 0 to plus infinity, and S sub k to be the kth partial sum. So sum from n equals 0 up to k of negative 1 to the n 1 over n factorial to n plus 1. Then, according to this theorem, we have the following. Then, the absolute value of S minus S sub k, this will be less than or equal to B sub k plus 1. So we just look at this, and we need the k plus 1 term. So this will be less than or equal to 1 over k plus 1 factorial times 2 times k plus 1 plus 1. Okay? And this guy here, we want this to be less than or equal to 0.001, because you want this error. This is the error term, S minus the kth partial sum. Okay? You want that error to be less than 0.001. So you want this to be less than or equal to 0.001. Okay? Following? Now let's just write this 1 over, let's write 0.001 as 1 over 1000. Is that correct? 1 over 1000, that's 0.001. Okay? And then we calculate. We calculate the value of k such that this expression is less than or equal to 1 over 1000. So we solve for k. Solve for k such that on the left-hand side of that part will be having k plus 1 factorial, and then the other factor will be 2k plus 3. Okay? So if you notice this one, you have 2k plus 2 plus 1. That's why you will have 2k plus 3. Okay? And then we want this to be less than or equal to 1 over 1000, or this means that we have k plus 1 factorial times 2k plus 3, this must be greater than or equal to 1000. We just need the smallest value of k satisfying this inequality. Okay, we need the smallest value of k satisfying this inequality. And since this is just a small number, 1000, let's just estimate the value of k. Maybe let's try k equals 3, k equals 4, or k equals 5. Okay, and check which one will satisfy, check the smallest number that will satisfy this inequality. Okay, so we try if k equals 1. If k equals 3, let's start with k equals 3. Then you will have 3 plus 1 factorial times 2 times 3 plus 3. You have here 4 factorial times 2 times 3, that's 6, plus 3, that's 9. So 4 factorial times 9. What is 4 factorial times 9? 4 times 3 times 2 times 9. This is 216. So it's not that k. If we have k equals 4, let's check this guy. Then you have 4 plus 1 factorial, 2 times 4 plus 3. So we compute this. You have 5 factorial times 2 times 4, that's 8, plus 3, that's 11. So 5 factorial, that's 5 times 4, 20 times 3, 60 times 2, 120 times 11. 120 times 11, and this is greater than 1000 already. Correct? This is 1320. So what does this mean? We just need k equals 4. Okay? So thus, we take k equals 4. We now solve. So the integral from 0 to 1 of e to the minus x squared dx, this is approximately equal to the partial sum, and from 0 up to 4, we take k equals 4. Okay, that's your s sub k in here. Okay, that's your s sub k, so we need s sub 4 of, you have negative 1 to the n over n factorial to n plus 1. So this is equal to, when n equals 0, that's just 1. So we have 1. Then when n equals 1, you have minus 1 over 1 factorial times 3. Then when n equals 2, you have plus 1 over 2 factorial times, so 2 times, where are we at? 0, 1, 2. So 2 times 2, that's 4 plus 5. 4 plus 1, that's 5. Plus, when n equals 3, we have minus 1 over 3 factorial. And then you have 2 times 3 plus 1, that's 7. And then when n equals 4, you have plus 1 over 4 factorial times 2 times 4, that's 8 plus 1, that's 9. Okay? So if we calculate this, what do we get? You have 1 minus 1/3 plus 1 over 10 minus 3 times 2, that's 6, times 7, 1 over 42, plus 4 factorial. What is 4 factorial? Times 9, so that's 216 in here. Okay, so 1 over 216. And this is approximately equal to, try to use any calculator, 1 minus 1 over 3 plus 1 over 1 over 10 minus 1 over 42 plus 1 over 216. So I hope we have this. Okay, and this one is, so the exact value that I got here, it's 5651 over 7560. And in decimal, let's compute this in decimal. 5651 divided by 7560. So in decimal, I got 0.7475. 7475. So approximately 0.7475 487. So let us use this decimal. Okay. So according to our computation, the integral from 0 to 1 of e to the minus x squared dx, this is approximately equal to this. Okay. Now, let me just verify the exact value of this. Okay. Let me verify the exact value of this. So again, the exact value, approximately, actually not the exact, but approximately equal to 0.7468. Our computation gave us 0.7474. So really close. All right. For this example, we want to find the Maclaurin series for f of x equals x squared e to the 2x. So again, we just use the Maclaurin series for e to the x, which is the sum from 0 to plus infinity of x to the n over n factorial. Again, valid for any x. The equality is valid for any real number x. So we replace x with 2x, and then we multiply the series with x squared. So in here, we have x squared sum, and from 0 to plus infinity. Oops, let me write this first. X squared e to the 2x. This is equal to x squared. Now we write the series from n equals 0 to plus infinity of 2x raised to n over n factorial. Or this is x squared sum from n equals 0 to plus infinity of 2 to the n x to the n over n factorial. And then since your x squared here does not depend on 0, we can bring it in so that we will get the series from n equals 0 to plus infinity of 2 to the n x to the n plus 1 or plus 2 over n factorial. So that's the Maclaurin series for that function. Okay. For our next problem here, we want to evaluate from 0 to 1 the integral from 0 to 1 of cosine x squared dx as an infinite series. So we first recall the Maclaurin series for cosine x. So cosine x, this is the sum from n equals 0 plus infinity of negative 1 to the n x raised to 2n over quantity 2n factorial. And again, this guy here, it's valid from for all real numbers x. Okay? So using this, we now write cosine x squared as a power series. Then we can do the integral from 0 to 1. Okay? So the integral from 0 to 1 cosine of x squared dx, this is now equal to the integral from 0 to 1 of the series. And from 0 to plus infinity, negative 1 to the n, then we now replace x with x squared. So we will have x squared quantity raised to 2n, okay, divided by quantity 2n factorial. For this guy here, it's the, um, let us interchange the sum and the integral. So you have the series n equals 0 plus infinity. Let us also bring out these constants. So negative 1 to the n over quantity 2n factorial. And then we integrate from 0 to 1, x raised to 4n dx. So this guy here, it's the sum from n equals 0 to plus infinity, negative 1 to the n over 2n factorial. We integrate this. This is x raised to 4n plus 1 evaluated, or over 4n plus 1. We evaluate from x equals 0 to x equals 1. And again, this does not have any constant. I mean, the whole series here does not have any constant. Okay? So at x equals 0, everything will disappear. We only have to evaluate at x equals 1. So when x equals 1, we will now obtain the series sum from n equals 0 to plus infinity of negative 1 to the n over 2n factorial times 4n plus 1. So this is the integral of from 0 to 1 of cosine x squared dx. Okay? Okay. So, oops. For this example, We want to find the third degree Maclaurin polynomial of g of x, e raised to 2 sine x, and then use the result to approximate g of 0.02. Okay? So first, we need to find the Maclaurin series for the polynomial. Okay? G of x. So we can do the differentiation. Okay? Since we only need the third degree Maclaurin polynomial, we'll just do the differentiation up to the fourth derivative, maybe third or fourth derivative, but let's see. Since we want Maclaurin, we evaluate each derivatives at x equals 0. So first, the zeroth derivative at 0, this is e to the 2 sine 0. Sine 0, it's 1. It's 0. So 2 times 0, that's 0. So e to the 0, this is equal to 1. First derivative evaluated at 0. So we get the derivative of this. We will have 2 cosine x e to the 2 sine x evaluated at x equals 0. But again, at x equals 0, this guy here, it's just 1. Okay? And then you will have 2 cosine 0. Cosine 0, it's 1. So this is equal to 2. So we have the constant part. We have the linear part. Let's look at the quadratic part. G double prime at 0. So we get the derivative of this. So 2 times left cosine x times derivative of right. 2 cosine x e to the sine or e to the 2 sine x. So that's left derivative of right plus right e to the 2 sine x times derivative of left. This is, what is this? This is negative sine x. And then we evaluate this at x equals 0. At x equals 0, sine x will be 0. So this will disappear. And then we will have here, this guy is 1. Cosine x and cosine x at x equals 0, that's just 1. So you will have 2 times 2. So this is equal to 4. Okay? And then, this guy, let me just rewrite this. You have 2 cosine squared x e to the 2 sine x. So if we get the third derivative at 0, this is what? We multiply this 2 times 2, so you will have 4 there. And then left derivative of right. So cosine squared x times the derivative of right, it's still 2 cosine x e to the 2 sine x. And then here, plus right, derivative of left. We will have e to the 2 sine x. Derivative of left, it's 2 cosine x times negative sine x. Correct? plus, for this guy here, left derivative of right, e to the sine or e to the 2 sine x times negative cosine x, then right derivative of left, you have minus sine x times 2 cosine x e to the 2 sine x. And then you evaluate this at x equals 0. So this guy here will disappear. I'm missing something. So I have to close this parenthesis here. That's from your 2 times 2. And then I have some 2 here coming from this. Okay. So plus here and then the 2 here. Then of course I have some 2 in here also. But anyway, at x equals 0, this will disappear. Okay. This will also disappear. This guy here, 4 times 2, that's equal to 8. And then in here you have 2 times 1 times negative 1. So you have 8 minus 2. So this is equal to 6. Okay? So for the Maclaurin polynomial, you have P3 of x. So you have 1 plus you have 2 x. That's 2 over 2 over 1 factorial. And then in here, plus you have 4 over 2 factorial x squared plus you have this 6 over 3 factorial x cubed. So if we simplify this, we will have 1 plus 2x plus, so 4 over 2, that's x squared, 2x squared, and then 3 factorial, it's 6, so 6 over 6, and then we have here plus x cubed. And then finally, g, so g of 0.02, this is approximately equal to p sub 3 of 0.02. So just do the multiplication here. You have 1 plus 2 times 0.02 plus 0.02 squared plus 0.02 cubed. Oops, I forgot the times 2 here. Okay? So we have this, and I tried to calculate this. I got 1.0, okay, let me use red here, 1.040808. Okay? You can also verify this. Now, the actual value, well, not really the actual value, but a more accurate value of g of 0.02, okay? I found that it is 1.040807999. Okay, so look how close we are. If you um, round this off, you will get 1.040808. Okay, the next value here, it's not 9. It's, I think, 4 or 2. But anyway, our value in here, p sub 3 of 0.02, is this, and it's really close to this approximate value of g of 0.02. Okay, so that's my last example. Thank you for staying. And if you have questions, feel free to ask them, send me an email, and I will answer as soon as possible. Okay?